Hey, good afternoon, Math 101 Hazleton, Justin Pashara here. Today I'm going to continue our discussion on the real numbers. In the first video on section 6.1 we talked about the real numbers and all the subsets that make up the real numbers. So if you remember, we talked about natural numbers, whole numbers, integers, rational numbers, irrationals, and all those numbers all together are put into what we call the real number system. So today what we're going to do is go a little bit one step deeper now. We're going to look at the real numbers as a system or a structure. And this is stuff that you will learn a lot more in detail if you took like an abstract algebra course or a number theory course or a course in topology down the road. But for now, we're just going to look at some of the basic things that real numbers exhibit. This will be part 2. And then next time I'll have actually a third video to finish out section 6.2, which is more on just the computational side. So that'll be the more easier stuff. While we don't touch a lot on this in 101, you still have to be responsible for knowing some of these properties that we're going to learn. And I'll be referring to the PowerPoint that I put on Blackboard for you guys as we go forward. So the real numbers, if you want the real long story made a little bit more short, is that the real numbers form what we call in mathematics a field. So a field is a term given to a set and operations that exhibit these qualities. So for example, the real numbers on addition and multiplication form a field. So these properties I'm going to list, which are ones that you probably will remember from high school, form what we call a field in mathematics. And there's more than just fields. We have rings, we have groups, integral domains, near rings, commutative groups, all kinds of stuff, but we just need the basics. So we're going to look at the field properties. So the first property we have in terms of field is what we call closure. So what closure means is this: if we have a real number A and a real number B, right? So A and B are considered real numbers. If A plus B gives us a real number and A times B gives us a real number, we would say that that set, which is the reals, is closed, right? So we'd say this is closed on addition, and we'd say the real numbers are closed on multiplication. So in other words, if we add two real numbers together, we're going to get another one back. And if we multiply two real numbers, we're going to get another one back as well. And that's not really far-fetched. Now, interestingly enough, you could break this down and think like this. Would the set of integers be closed? Meaning, when you add two integers, do you get another one back? When you multiply two integers, do you get another one back? Notice that subtraction is not part of this deal here, because sometimes subtraction doesn't guarantee things, and we'll see that upcoming. So the first field property is what we call closure. The second property is the commutative property. So one of the field properties is that addition and multiplication are commutative. So for example, A plus B is the same as B plus A. Meaning that when you add two real numbers together and you change the order in which you add them, it still gives you the same result. So for example, 2 plus 3 is 5, which is the same thing as 3 plus 2. Okay, that's something that takes you back to elementary school. And also, AB is the same as BA, meaning that when you multiply A times B, that's the same thing as doing B times A. For example, 2 times 3 is 6, which is the same as 3 times 2, which is also 6. So that's your second property. The third property, that's a field property, is the associative property. So what does the associative property say for real numbers on addition and multiplication? It says that if we do A plus B plus C, with the parentheses around B plus C, that would be the same thing as saying A plus B first plus C. So in other words, the associative property says that we could go ahead and group these things differently as long as we're adding them all, but we'll still get the same result. And the same thing works for multiplication. If you have A times B times C, where we do the B times C first, that's the same thing as doing A times B first and then multiplying it by C. Okay, so that's the associative property. And you can make up an example of your own if you want. You know, pick numbers A, B, and C and go ahead and group them differently, and you'll see you get the same result. So we have closure, commutative, and associative property. What else do we have here? Well, it gets a little bit more interesting as we go down the list. So after the associative property, we have what we call the identity property. So the identity, we just have to be a little more careful based on what operation we're talking about. So for addition, the identity would be like this. A plus 0 is the same as saying 0 plus A, which gives us the result of A. So the identity says on addition, so the identity on addition says that if you take some number A and add 0, we get back A. 1 plus 0 is 1. Negative 2 plus 0 is negative 2. But then we have the identity on multiplication. That works a little bit differently. That would be A times some number 1 gets us back to A. So in other words, the identity element for multiplication is 1, because when you multiply any real number by 1, you get that real number back. But the identity element for addition is not 1, it is 0. 0 plus the number you started with gets you back to where you started. So that's the identity property. And then the next property we have is what we call the inverse property. And that works two different ways as well. The inverse property on addition says that if you take some number A and add something to it, you're going to get this number 0, which was your identity element. So what would that have to be in this case? A plus what number would get you 0? Well, it would have to be opposite A. A plus a negative A, for example, gives you 0. So an example would be like this. 2 plus negative 2 gives you back 0. That would be an example. Negative 2 would be considered your inverse element. Now, how does the inverse work on multiplication? Well, it's a little bit different. A times what number is going to get us to 1, right? So what number serves as an inverse when you multiply it by A to give you 1? Well, you have to think fractions. It would be 1 over A, or the reciprocal of A. So for example, let's say we have 2 times what is going to give you 1. Well, that's going to be the reciprocal of 2, which is a half. So you just have to be a little bit careful here with inverses and identities. Each one has its own unique case. So you just got to be a little bit careful. A good question that I posed to you in your PowerPoint says, do these properties hold for subtraction or division? So that's very good to think about if you have some time, right? Which we all kind of do now, unfortunately. And if you want to think about this, do these properties hold up under division or subtraction? And I think you may be able to answer that without doing too much extensive work. We have one more property then. This will be property number 6. And this is what we call the distributive property. So a field is also distributive, meaning that if you have some number A times some numbers B plus C, we can write this as AB plus AC. In other words, what we do is we distribute or multiply the A through to each element. That's what we call as a distributive property. So what forms a field? When you have a set, in this case it's a very specific set, it's the real numbers, but again you can take this out to other sets of numbers or the generic set, like we call it F. So a field is a real number, a set of real numbers in this case, and an operation addition and an operation multiplication that exhibits the closure property, commutative property, associative property, identity property, inverse property, and the distributive property. Those are the things that make up a field. Now in your PowerPoint, what you'll notice is that I went steps in front of that. We could write something called an ordered field, which means we could go ahead and put some other properties into play, which you'll read in your PowerPoint, that has to do with ordering mechanisms, which is something that's kind of common sense in a way. We know on a number line we could order numbers from smallest to biggest, right? And that has to do with a little bit of it. And then the whole grand scheme, the real numbers on addition, multiplication, and when we put this ordering device in, make up what we call a complete ordered field. So it's like the granddaddy of all systems. It has everything anyone could ever want to have in an algebraic system. And that's something that's a little bit beyond us. I'm never going to ask you on a test or quiz about that. But that's something that's interesting. And if you have some time, you could look this stuff up. It's kind of neat for those that want a little bit of stuff that goes beyond this. For some of you, this is more than you'll ever need ever. So what I'm going to do is just a few examples on this, and then I'll end this video, and then we'll go ahead and I'll make one more video for you in the future, which will have to do with order of operations and more of the mechanical computational side of things. Some of the homework exercises you'll see here test your ability to use these 6 properties. So enjoy doing those. Don't stress yourself out, of course, over them, but there's some good thinking questions, and there's some basic ones too. But here's some examples. We'll see if we could go ahead and figure out what property is being used. How about something like this? If I say pi is a real number, -2 is a real number, so pi plus -2 has to be a real number. Do you know what property that would be illustrating? If I say pi is a real number, -2 is a real number, so pi plus -2 is a real number. Do you know what property that would be? If you said the closure property of addition, you'd be correct. And for me, we're just going to make this easy. We'll just call this closure. It doesn't matter about the plus or the dot multiplication. It's the closure property of addition technically, but we can just say closure. How about if we have something like this? 2 plus 7 plus 9 is the same as saying 2 plus 7 plus 9. So we have all the same numbers there. What did I do to make this look different? Well, notice the parentheses are around different numbers this time on each side. So that means we don't care about how we group them. We'll always get the same result. This would be associative property. That's the associative property. How about something like this? If I have -44 plus 44 equals 0, what property is that illustrating? Well, I have -44. I'm adding something to it to get me to 0. And remember, 0 is the identity element for addition. So what is this going to be? This is going to be the inverse property for addition. 44, number 44 acts as the inverse. And we'll do one more. How about something like this? How about 14 times 1 equals 14. This would be the identity property for multiplication. So that's the identity of multiplication. Okay, so I think that's good for now. Try to break this topic down in little pieces for you. So I'd urge you to go back, watch this video, see if you can redo the examples. This takes care of the properties part of this chapter. The last video you'll see in this series is going to be on order of operations, adding and subtracting, multiplying, dividing integers and other real numbers. And that'll be coming up shortly. So when you have time, start getting started on your homework. And if you have questions, let me know. I hope everybody is doing healthy well. I hope you guys are all sane. And until next time, I hope everybody is well. And I will see you when I see you.